So I just wanted to start with some pictures of animals hugging each other, because I know for myself, at least, this is a very anxious time and stressful, and also pretty deeply disappointing, especially for those of you who are graduating this semester. This is a really, not what we had hoped the semester would look like. We're going to get through this. All of us at the university are here to help. We're going to be as flexible as possible moving forward. We're going to try to have more help hours, online office hours. So as much as we can do, we're gonna work with you guys to get through this. My request from everybody is to help us help you too. So if you're running into issues, whether that's problems with the labs themselves, probably like sort of technical issues in terms of getting GIS installed or connecting to GIS as that's sort of evolving, try to deal with those things before, like a few days before due dates. It's a lot easier for me to help troubleshoot if you email me on Wednesday when the deadline is on Friday, rather than at like 5 o'clock on Friday. So just try to build in a little bit of an extra buffer in terms of like getting into the labs and starting to think about final project stuff. Before we talk about those various announcements and stuff, I did want to show you this map, which is actually an example of really good cartography, I think. So they've got an equal area projection that they're using. This is this morning's numbers of cases in the US. They also have this nice graduated color that they've used on there. So, generally props to, I think this is Time magazine, but whoever created this particular map. You guys may have seen, I was going to show you the other one that's like that global one that's been going around, which has a Mercator projection. And so Africa looks really small and, like everything else looks really huge. But, rather than showing examples of bad coronavirus cartography, I figured we'd show examples of good coronavirus cartography, because there are some, good things out there. Okay, long litany list of announcements. So we are going to be using Zoom a lot after spring break and starting today. So I've got, this little thing that you guys in class can see at the top of there that has the like green and red thing. That's what it looks like when you're in a Zoom window. So we've got a dozen or so people online on Zoom right now. I'm also recording this lecture, so hopefully that's picking up my voice as well as the slides, so that we can post this on Moodle and you guys can refer back to it. I've also added a discussion group to the top of Moodle, so that list is getting a little bit long, but there should be a discussion for Lab 6 at the top of Moodle. When we get to Lab 7, I'll add a discussion forum for Lab 7, and so those are basically the grad TAs and myself will be kind of checking in on those on probably a day-to-day basis. So not necessarily like instant responses, but if you're running into, issues and you want to post them in the forum, then that'll share with everybody kind of general issues that you might be running into as you're working on things kind of outside of the scheduled lab hours. I have a Google Sheet that I'm working on right now that is links to Zoom sort of recurring meetings. So basically what that is myself, the grad TAs, all of the undergrad TAs will have an online face-to-face meeting where we're just going to be like sitting there waiting for you guys to come to us to ask questions as you're dealing with it. How many of you guys have used Zoom? Okay, so that's about half the class sitting here. I'm going to guess everybody online has now used Zoom too, because they're in Zoom. You guys are going to get really familiar with the software kind of starting day one after spring break. The nice thing about it is that it's fairly user-friendly. It is, it works, it's not as kind of buggy as Skype is. So Skype has those kind of things where if your connection isn't as good, then sometimes it breaks down a little bit. Zoom is less buggy in that sense, although we're going to test the heck out of it after spring break when the entire world is on Zoom collectively. The other nice thing about it is that you can share screens very easily on it. So that means that if you are on a computer and you're running GIS and you're saying, what the heck is going on? I push this button and nothing happens. You can share your screen with me, with one of the undergrad TAs, and they can kind of live look at your desktop at what's going on and troubleshoot. That doesn't mean that the system is perfect. Some of the things that we run into pretty regularly in hosting meetings is stuff with sound. So if your volume is on and somebody else's volume is on, sometimes you get some like feedback loops and stuff. So just be patient with it until you kind of get used to working with it and get used to where different buttons are and stuff that you're going to push. We will in lab this afternoon and tomorrow afternoon be going over we're going to open a Zoom window and show you guys what the interface looks like, just so for those of you who haven't interfaced with it too much, you'll have at least a little familiarity with what to expect when you're getting online. So as of right now, everything's normal for today and tomorrow labs, as far as I know. So come to Thursday afternoon lab, Friday morning, Friday afternoon labs. We will be there in person. The schedule is that lab 5 is due by the end of the day tomorrow. So that's your editor lab where you're making the maps of campus. Probably about half of you guys have already turned in lab 5 and about half are going to be finishing up lab 5 this week. The main thing that you're going to be working on in lab this week is lab 6. So this is the raster spatial analyst lab. This is sort of the transition that we have from working primarily with vector data and our points, lines, and polygons to moving into raster data where we're really focused on pixels. So that's what we're going to be talking about mainly today and what you're going to be working on in lab this week. Luckily, lab 6 has an extra week buffer kind of built into it. So lab 6 is not due the Friday after spring break. It's actually due on April 3rd. So it's sort of like 2 weeks after spring break. So there's a little bit of some wiggle room in here for us to work together to figure out how to deal with this kind of online stuff. I said this already, I will be posting all of those Zoom links as I have them for the TAs and everything in terms of online help after spring break. This isn't actually in the text, but one other thing to look out for is I'm going to be sending out an email with a web form for you guys to fill out, so basically a poll. Because what I need to find out is who does not have access or will not be able to access the software from home. Anyone is welcome, everyone is welcome to install GIS and get a student license from Lara or from Amanda, provided that you have access to a computer that can run Windows. So whether that's laptop, desktop, either of those is totally fine. A Mac, if you can run Windows on it or run Parallels or something like that. For folks that do not have access to either of those options, we're working with IT to try to get you guys remote access into the computer labs. But keep an eye out for a web form from me, basically, because I need a head count on who needs access for remote access. Definitely it'll be easier on IT if we can send them a list of names rather than trying to do it for the entire class, basically. Okay, and actually that sort of leads into the next one. So if you can install GIS, so if you're going home and you've got access to a desktop computer or something like that at home, think about installing GIS on there. That will definitely make things easier if it's possible. And you can email Lara or Amanda for that access code. Their emails are on the syllabus and also at the top of Moodle. I guess I already said all of those things. So I thought that I missed doing that, but in fact, I had that in there. Excellent. Any questions, concerns at this point? What are you guys thinking? Okay, that's good. Yeah, what you got?
Well, I mean, I don't really have very good Wi-Fi in my house, so
okay.
I'm not sure I'd be able to do Zoom.
Okay, so internet, so I'll put that on the web form as well, the internet question, and we'll figure out how many people are going to run into that and work around as best we can. So
I mean, I don't think this applies to everybody, but I'm trying to work since I'm going home.
Mm-hmm.
It's like I have utilities to pay and stuff.
Yep.
And I work like 8 to 4, so it kind of like, I have to like go, home like early for my shift.
Okay. So we can, so if we try to do some like evening hours or something like that, as far as extra help, that might help things. Okay, that's good to hear. I will try to put on the web form, I'll put also like a suggestions, fill in the blank kind of thing. So add me things in that blank form. That's what happens when I try to write and speak at the same time. I was also considering, oh, sorry, go ahead, yeah.
Yeah, I asked for lectures, so they're all going to be through Zoom. Is this something that we could like watch kind of leisurely on our own time, in the sense of like we don't have to be here directly at 11:30?
Yeah, perfect. So that was actually my next question too. So what I was considering doing is pre-recording the lectures on Zoom and then posting those on Moodle. And then just having basically like open office hours or question hours during that 11:30 to 12:45. My office hours are normally 1 to 2 anyway, so I can try to just do, big chunk of office hours as a general rule on Thursdays, where I'll just be like on the Zoom thing to help with whatever is going on. So does that sound like does that fit everybody better versus like live streaming lectures? Okay, so I will plan to pre-record lectures from here on out and get those posted on Moodle so that you can see them. Yeah.
I heard somebody that the library might be open. No, that's true. Or if you will be there.
I do not know yet. As far as I know right now, what they have told us is that faculty and staff can have access to things, but students are supposed to be off campus. But if if you live in Amherst and accessing computers is an issue, I feel like that is one of those exceptions that they should be making, basically, so they are trying to, I know that there's a general announcement that's saying, for lab courses, we're trying to like help people as best as possible. And so if there's occasional access to computers would help that situation, then that's definitely something that, that I can raise to the best of my ability anyway. There's not a whole lot of people there's not like a point person at this point. We need a coronavirus czar. But put that in the fill in the blank on the web form. Fill in the blank is what I should write here. Okay. Any other questions, concerns, things you guys want to raise? So bring questions and concerns also to lab, because this week especially we want to try to get you guys as comfortable as possible with whatever is going to happen after spring break. So to the extent possible, we want to know what all of the problems are so that we can be working on addressing them with IT over this next week. Awesome. Okay, so I actually really love working with raster data. Spatial analyst is the name of kind of the toolbox that has a bunch of these spatial data sets that deal specifically with rasters. So spatial analyst is the new kind of toolbox that you guys are going to be learning about this week. Before we get there though, just one sort of tip for today is this, for those of you guys who have online access at least, there is a nice feature in ArcGIS that's called ArcGIS Online. And ArcGIS Online, so for example, if you wanted to have like an aerial photo backdrop to the map that you're trying to create, or if you're looking for data, sometimes this is a good source of data, although it's like a huge morass in some ways of data. It's kind of hard to like get through. But you can, from the ArcMap interface, go to add data and add data from ArcGIS Online. And that will bring up a new window that looks something like this. And then you type in whatever keywords you're looking for and add those data. So imagery and base maps tend to be the ones that I use most often for ArcGIS Online, because they're just sort of like a nice background to whatever it is that I'm looking for. The drawback of this though is that in many of these cases, the maps that you're adding are not actual data that you have access to. So it's just kind of a backdrop to whatever your map is that you're building on top of it. So the negative of that is that you don't necessarily have the ability to change the cartography. It is whatever it is. And sometimes the cartography is not exactly what you would like it to be. In other cases, though, if you sort of search through ArcGIS online, you can find cases where people have posted actual data that you can download. So it's not only kind of a map that sits behind the scenes of whatever you're working on. It could also be, you know, actual data that somebody has posted, made available to everybody that you can download and then work with for your final projects or for whatever project you're working on. So that's going into this too. So typically those base maps, if you're looking for a base map, the raster data that shows up in that as sort of a backdrop, it looks a lot like Google Maps would look, you know, in terms of you zoom in and out and you see this sort of satellite image scaling down to some sort of aerial photo type of thing. But typically you're not able to download those images. They just kind of like sit in the background. If you want to download them, you would need to go to a different source of data. Oh, you know, actually, I forgot to say in my various announcements earlier, but for final project stuff, I have now posted a web form at the top of Moodle for anybody who's interested in looking through the ideas for final projects. I'm going to be reminding you guys about this the Thursday after spring break during lecture or during the online lecture or in Moodle and stuff. I'll try to put it in as many places as I can. But leading up to the assignment that's due on April 10th, so, you know, we're like a month out at this point, but it'll come kind of fast. That's the one that is your methods outline and your study area maps leading into the final project. So by about a month from now, you guys want to have a pretty solid idea. Yeah, I would say a pretty solid idea of what you want to do for your final project. You don't have to have all of the steps lined up at that point by any means. That's part of what we do. That's why we have the methods outlined so that we can help you figure out what those are. But just an FYI, that web form is up. There are 6 or 7 project ideas that were proposed by graduate students or faculty where there's only like one spot available. So if you see one of those ones that says proposed by faculty and wherever or grad student, and you want to do that one, try to fill out the web form early so that you get first dibs on whatever that project is. Okay, back to the raster data. Okay, so here is the Quabbin and a real zoom in on peninsula in the Quabbin, and where you can start to see those pixels, right? And so the question is, what's in that pixel? So if you click on that pixel, if you use the identity tool, like what do you get? Yeah, Eric.
Is it like the color or the shading of it?
Yeah, what is it? So what represents the shading?
Like what does the shading represent?
Yeah.
Like the darker is water and the lighter is land.
No, you're absolutely right. And so if you click on that, how does ARC know like darker versus lighter to represent it in this way?
Sure.
Any other ideas, Sean?
Well, photography, every pixel is actually data.
What kind of data?
Whatever. I don't know. The GK, well, this is shot in different formats, like raw is different than.
Yeah. So what's the data of any single pixel? You guys remember back from lab 1 when you did the aerial photo? Every pixel has an area, but if you click on it, it'll have some other thing associated with it that tells ARC the color, this one black in color, this one gray, and this other one white. Any other ideas? So basically all of these pixels are numbers, and that's it. It's a numeric value. And anytime you see a representation of, sorry, I need to stand closer to the mic so that the online people don't lose me. Anytime you see something that looks dark, black, basically the value of that is something that's low, like 0, for example. And anytime you see something that's brighter, like white, then the value of that is something high, like 100 or 1,000 or 10 million, or, you know, like it could be any numeric value that whoever created this image chooses for that particular image. So in grayscale, you know, like we can imagine that, you know, like, okay, these numbers go from 0 to, let's say, 1,000, right? So 0 is represented as dark colors and 1,000 is represented as really light color, well, gray, and everything in between is something between 0 and 1,000, whatever it is. So if you use that identify tool and you clicked on one of these pixels, the thing that, you know, you wouldn't have like a whole bunch of attributes that come up for it. The only thing that you get is, you know, this value is 63 or something like that. It's interesting then to think about a color image, right? Because we're used to thinking about color images all the time. So that same pixel, if we're talking about color, is rather than being one single color, you know, one single color in grayscale or one single value in grayscale, is actually made up of several, or several being three, of three different grayscale values that collectively make for a color. So generally there's a red, there's a green, and there's a blue in the visible spectrum. We're going to talk more about remote sensing after spring break, actually. So, you know, there's more than just what we can see. And, you know, if this pixel, whatever pixel we're pointing at, looks mostly green to our eye, then that's probably because the green value, numeric value, is higher than the red and the blue. And in fact, we can kind of look at that and say, well, it's kind of like greeny yellow, that tone. And actually, counter to like the crayon method, but actually if you add red and green, you get yellow in sort of a brightness spectrum. So this is green with a little bit of extra red, and so that makes for more yellow. We'll talk about color also after spring break. And not too much blue in it, so, you know, more on the green to yellow side. So anytime you open a raster data set and you look at all of those different pixels and you zoom way into them, ultimately each of those pixels has some sort of numeric value to it. This is a very hokey grid that is obviously not a raster, but it's just to represent, you know, that you would have a number associated with each of those different pixels, and that a raster grid tends to look like, you know, that weird, I don't know, like muffin tin format. I feel like it kind of looks like a muffin tin to me. You guys know this already, that raster data are made up of pixels, right? So whereas vector data are all based on vertices or points, raster data are always built on pixels. The pixels are always square. And generally we have this kind of like weird way of representing pixels or describing pixel area, I guess I should say, in that we only talk about pixel size in terms of one axis, so like the height or the width. So if a pixel were 10 meters by 10 meters, and that has a 3 on that just to be like, that pixel has a value of 3, whatever. 10 meters by 10 meter pixel, we would call that a 10 meter pixel size, even though the area is what? 100, yeah, 100 meters squared is the actual area of a 10 meter pixel. This is going to be important because later, as you guys know, you can calculate area of a polygon, right? By just telling GIS, calculate the area of this polygon, and out pops the area in whatever units you want it to be. For pixels, that is not as easy. Instead, we have to know the size of the pixel, and that is your handy source tab. So this particular pixel of whatever this grid was is a 28.5 meter pixel. Yeah, Kelly.
Are they always equal to like even if it's like projected to it, like it's seen, it's not, or like, because it wouldn't change the size, right?
If it is not square, I would say that's really rare, but I'm not going to say it's impossible because I'm not actually sure that it's impossible. But it should tell you in the source tab. So if you have If you have a raster grid and you're trying to calculate area and it's in a geographic coordinate system, no, not possible, right? Because geographic coordinate system, these units would be decimal degrees, and like you can't, decimal degrees are not units of distance, and so you can't calculate area in that way. That would be a rare case, I guess, where you would actually do that thing that we talked about in lab 4, like don't ever do this, which is to convert or reproject a raster grid from a geographic coordinate system into some sort of projected coordinate system. In lab, the only raster grids we're going to give you are ones in projected coordinate systems, so you shouldn't have to worry about that. But that is a really good question, and that's sort of why understanding the difference between geographic coordinate systems and projected coordinate systems is important for many different applications later on. So in this case, it tells you the cell size, it tells you the X and the Y, they're both the same. So this is a square pixel and it is 28.5. There's one other piece of information you need to know here, which is 28.5 what, right? So we know it's not, well, we hope it's not decimal degrees, otherwise it would be like one giant pixel for like the entire Western Hemisphere or something, right? But remember that in your source tab, you can also scroll down to figure out what the projection is, and the projection will tell you what the linear unit is. Most of the time these days, and for everything that we're going to be giving you, that linear unit is going to be meters. So just about every state plane and UTM projection, with the possible exception of Rhode Island, is in meters these days. So that's probably a decent default assumption, at least as you're working through labs. But all you have to do is scroll, and I'm sorry, I can't scroll down because this is a screen capture, but if you scroll down on this particular window, you would find whatever the projection is and the information about the linear unit so that you can calculate the area of a single pixel. So basically calculating area in raster means first you need to know the area of one single pixel, which you can get by multiplying the length times the width. And then you need to know the number of pixels that you're interested in. So how many are true for whatever it is that you're trying to do? How many of these pixels are trees or forests or whatever? How many of these pixels are urban areas? And then you need your calculator to multiply those two things together. So different way of calculating area for raster versus vector. Another thing to bear in mind, because you guys are going to be creating raster files for lab 6, is that the pixel size matters depending on what your application is. So this is a vector shape of a snake, I think. It looks, can anybody identify that snake for me actually? No? Anyway, this is a vector file of something. And this is a conversion, so you guys are going to do some conversion tools from vector to raster to take this value, because this whole thing, right, has a single value, and convert it into raster. I'll see if I can get the ladybug to move. No. If you choose a largish pixel size relative to your shape, then you're going to get what we would probably refer to as pixelation of whatever that shape is. You're missing the kind of nuance of the different curves. If you choose a smaller pixel size, so the one on the right, then you're going to get more nuance of the feature that you're trying to represent. The trade-off between those is that raster 1 takes very little space, very little memory, because the pixel size is large. Raster 2 is going to take a little bit more space and memory because you've got more pieces of data that you're asking the computer to represent. So that's always a trade-off. And that's basically the answer to why, typically we don't use 1 meter pixels, small pixels to represent the entirety of the Earth, because basically GIS will choke on it and die a sad death, like of trying to input meter squared for the whole world. That said, we've come a long way. So, if I'm giving the same lecture 5 years from now, that may no longer be true. Maybe all of this stuff is going to be up on cloud computing and everybody can handle sub-meter squared pixel sizes for the entire Earth. So computers are rapidly changing. But generally what we do is that if we're trying to represent a larger area, and that's why as you guys go to Google Earth or Google Maps, you would see if you're zoomed to the whole Earth, it's kind of a, you know, you can't see the little details, and then you zoom in and you kind of see that the types of data are changing as you zoom in further and further. That's because basically Google Maps has this kind of pyramid scheme where they say, okay, if you're zoomed way out, we're just going to show you the coarsest resolution. You don't need to see the tiny details. And as you zoom in, we're going to give you different data layers that are more appropriate for those particular resolutions. All right, so advantages of raster data are that they represent a full surface. So within the entirety of that raster grid, you're going to have a value for every single pixel. The value could be no data, but there's never going to be a place where there's nothing, no information there at all. Big advantage of raster data relative to vector is that the size is much smaller. So if you have a raster representation of land cover, something like that, and you compare it to the size of a vector representation of that same thing, you're going to have, you know, maybe like 1/10 of the file size. Much easier for GIS to operate in raster land than in vector land. A lot less information for GIS to deal with, right? Because if you're in vector land, you have to remember all of those attributes, you have to remember all of those vertices and how, you know, what the geometry is between them. In raster land, all you have to do is say, like, here's my starting point of this whole grid, here's the number of lines and rows, here's the size of all those pixels, and here are all the values of them. That's it. And I probably said more things for there than for the vector, but like that's actually pretty simple in computer land for a computer to deal with, you know, essentially a matrix of numbers. It's like what computers have been doing since the dawn of computing time. The other nice thing about raster data is that they tend to look pretty nice on a map. So as long as you're not zoomed in and you don't see pixelation, they are continuous cover over stuff, so they can make for a nice kind of background base map. Disadvantages of raster data. So you guys know this already from lab 4, but changing the projections will fundamentally change those numbers and change the location of your pixels because they have shape and area, distance and directions. Those can all be distorted by reprojecting them. So try not to, unless you're in one of those situations where you need to calculate area and you're in a geographic coordinate system, that would probably be the only case where I would say it's okay to reproject, to use a raster reproject, basically. All other cases, try to avoid, because you're always gonna mess up your data at least a little bit. I don't even know what this is. I think this is a zoom in of topography somewhere in the Western US. A disadvantage of raster data also is that if you zoomed way in, then you start to get pixelation and then it looks funky. You know, it's hard to tell exactly what's going on. Okay, so types of raster data that exist. One type is continuous, right? So if we were talking about that aerial, that satellite image of the Quabbin, for example, and we said for argument's sake that the values go from 0 to 1,000, that would be an example of a continuous scale, right? So 0 is low, 1,000 is high, and you could populate it with all the numbers, 0, 1, 2, 3, up to 998, 999, 1,000, right? All those values are available. So examples of those types of continuous data sets include topography, right? So we can go from sea level all the way up to the top of Mount Everest, and we can populate every single value between those things. Satellite images or aerial images or drone images, any kind of remote sensing image is basically measuring how much light is reflecting back to that sensor. And so those go from something really low to something really high. Distance grids, which I'll talk about in a second. So basically distance you can measure in rasterland as distance away from all of these different objects. So if I created a distance grid away from me, it would basically look like a buffer, except that every pixel would have a value of 1 meter, 2 meters, 3 meters away from Bethany, basically going in all of these different directions. So that is a distance grid, could be everything from low, like exactly where I'm standing, to high, you know, practically infinity away from where I'm standing. So examples of continuous, here are some examples of discrete. So discrete, the most basic form of a discrete raster data set is a binary data set. So one that just contains zeros and ones. That's it in the data set. So you click on any of those pixels and the pixel will only ever have a value of 0 or a value of 1. There are also discrete data sets that have sort of a few values. So you might have low, medium, high, right? And that those would be coded as 1, 2, 3 or something like that. As you start getting to have more discrete values, then there's sort of a fuzzy overlap between what's discrete and what's continuous. So generally the ones to think about are ones where you have binary, 0, 1, or 0, 1, and 2, or something like that as the extents of your options. The reason that we have something like a binary data set generally is if we're trying to do habitat classification, for example. Let's say we want to identify the areas where a bunch of things overlap, right? So you say, I want to know areas that are forest, that are within, a couple hundred meters of wetland areas, where this critter has been seen previously, or like within the range of that. Then you could have all of those in binary data sets, right? Where 1 means true. True, this is a forest pixel. True, this is within 200 meters of a wetland pixel. True, this is within the range of where my critter has been seen previously. And in rasterland, and we're going to talk about this more in a second, so you'll see an example of it. In rasterland, basically, how do you combine a bunch of overlapping ones? Well, you do it with math. You multiply them all together, or you add them together, and you say, well, if I want to make sure that it is forest and close to a wetland and within the range of this critter, I'm going to multiply those 3 rasters together, and anywhere that I get a 1, it must have been 1 for all 3 of those, because otherwise I would get a 0, basically. So living in rasterland means math, pretty simple math though. I mean, we're talking about like 6th grade math here, so no fretting about that. And basically thinking in terms of how do you combine zeros and ones in ways to get the output of the suitability analysis that I'm looking for. In terms of continuous to discrete, there is a tool that you guys are going to learn called reclassify. You can always reclassify continuous to discrete. You can say, take all the values that are between 0 and 100 and call those 1. Take all the values between 101 and 200, call those 2. Take all the higher values and call them 3. Off you go. And you have a discrete binned grid. But you can't do that in reverse, right? Because you've lost the quality of those data. So you can't go to something that has 1, 2, 3 and say, like, now recreate that was actually 150 or something for this value in between. That information is lost. All right, so just in terms of some examples of stuff that you guys are familiar with looking at versus stuff that you guys are going to start seeing more of this week. Lots of buffer analyses that you guys have been doing in vector land. The raster equivalent of that is a distance analysis. And it's actually called Euclidean distance, just to make things complicated. There's lots of different ways that you can do distance analyses based on other stuff that we can talk about if you're interested in that kind of stuff for final projects. Euclidean distance is the most basic, which basically is just like, as the crow flies away from this thing, how far away am I? One thing to notice though about this versus the buffer is, remember the buffer like makes a shape kind of like around whatever distance it is. The distance grid basically just says, as its default, it says, I will take the extents of that line feature in this case, So the grid only extends to the boundaries, it doesn't extend beyond them. You can change that. There's an option to say, actually, I want to go further out than this, or set my distance grid to be similar to this other extents or shapefile. And there's a second step, right? So when the buffer, this is basically what you're treating this in vector land as basically that binary pixels, right? Inside the buffer is true, outside the buffer is false, right? In raster land, each of these distance pixels has a unique value to it. And so you actually have a two-step process if you wanted to create the equivalent of a raster buffer, which would be first to create a distance grid and then to reclassify it so that everything that's less than this far away from, you know, a distance less than 200 gets a value of 1, everything else gets a value of 0. You guys are going to be doing in lab also some topographic analyses. So those include pretty cool things actually, like creating a hill shade, which is an image, like a shaded relief map. You guys are going to be figuring out how to create slope maps. So from topography, GIS can automatically create slopes for you. It can also create aspect, and aspect is basically the direction of that slope. So is this a north-facing slope? Is it a south-facing slope? Is it east? Is it west? And some other surface analyses. So it could make like contour lines for you if that was something that you wanted to have for a final map. There's another fun thing that you can do if you've got a hill shade. So a hill shade is the one on the left, and the topography layer itself, the original topo, is the one on the right. And that is, you can combine them. Hope you guys appreciated that. That's like the best that I do this whole semester. I like worked really hard on that. So you can use some transparency. You can put those hill shades behind it to give it a little bit of that nice 3D effect. Okay. So I just wanted to talk briefly about, let's see if I can do the whiteboard over here. That's a nice whiteboard. Interesting. I can see my whiteboard, but you guys can only see the other thing. That's kind of fun. Okay, that sort of worked, at least for everybody in the class, and we will see. I don't know if everybody online can actually see it. Okay, but basically, let's not use a yellow one. Hang on, I'm going to see if I can project. Can you guys online just briefly, can somebody chat to me online and tell me if you see a whiteboard? Sorry guys, this setup is not super awesome. When I get this into my actual computer in my office, this will be a little bit easier, because right now every time I touch the touch screen, it like goes to a different thing. Where's my chat?
Is it under the More tab?
Yes, thank you. Okay, they can't see the whiteboard online. All right, so what, I think though I can draw on some stuff. Can I just like draw on here?
Yeah, I'm watching it now.
Okay, that's kind of fun. Then let me do a black screen. Yeah, okay. All right, this is going to be very hokey because if I touch the screen, it like flips it to the other thing. So basically what we want is, so I'm going to try to draw a really like terrible thing in black. Here's my, imagine these are pixels in a nice array of 3 by 3 with our lovely Windows background. It's very nice for like all of this. So the idea is, let's say, for example, that I have in these some soil information. Okay, so each of these pixels has soil information, and let's call some of these, I'm putting an S for like sand, and a C for clay. Ugh, painful. Okay, so I've got S's and C's over here, right? So let's say I've got that piece of information for my 3 by 3, and then I've got another 3 by 3 over here. And in this case, I have information about, let's say, there's a road that is like, here's the road. And now I want to know like distance away from roads, right? For whatever the habitat is of this critter. So this is going to get a 0, right? It's like on a road. These ones get 1s. Maybe this is a 2 for reals. And 3, and that's impossible. Whatever else goes on further away. I can probably do, no, I can't do a 4, etc. So the question is, all right, so now we've got a critter that we have some information about distance to roads, and we have some information about the sand versus clay and the soils, right? And so the question is, what do you guys think? Is the habitat, and this is like whatever critter you guys want it to be, is the habitat for that critter better further from roads or closer to roads?
Usually further.
Further from roads. Okay, so we're going to assume this is maybe like a critter that could get hit by a road or something like that, or hit by a road. Hopefully nobody gets hit by a road, hit by a car, and so we don't want to be close to a road. All right, so what do you think then? How far away from the road do we need to be? 4 units, 3 units, 2, 1, 0? 2 or more units away from the road for us to like be safe for this critter. Okay, so then let me do a red. So basically that says like, okay, this chunk over here, like this is like good for the critter, right? Okay, then how about sandy soil versus clay? What is your critter like? You just have to pick one. Sand, okay. Critter like sand, hates the clay, gets its paws stuck in that. So here's our basically like good stuff for this critter in sand. So visually, where are the pixels that are like optimal for this critter's habitat? Top left, yeah. So we've got like optimal habitat. You guys can see visually, give me some yellow, is like this stuff, right? Because this is the area that is basically sand and far away from a road, right? So what I just said, that and is important here if you're thinking about those. So and is actually a statement that you can use in GIS. It's called a Boolean operator. And or are both examples of Boolean operators. So if you put into GIS and you said, I want sand and far from a road, then you would just get out a true, false, so a binary, a 1, where 1, these would all be valued 1, and these would all be valued, well, those would also be valued 1, and everything else would be valued 0. So the trick, though, is that right now we have this in terms of S's and C's, and we have this in terms of 0, 1, 2, 3, 4, right? So in order to actually do this in GIS, let me try white, maybe that'll show it better. What we would need to do is convert this into a grid of the same size, obviously, and depth and whatnot, where instead of this being S's and C's, this would be, okay, we said sand is good for the critter, right? So these would be 1, 1, 1, 1, and then everything else would be 0, etc. across 0, 0, 0, right? And we would do the same for this thing, where in this case, our grid looks like, so in this case, we're reclassifying everything that's greater than or equal to 2, and we end up with 1, 1. I'll just draw a nice long 1 there, nice long 1 here, and a 1 down here, and then these guys are zeros, right? And so then it depends on what your operator is, like what your output is here, right? So I have 2 main options of things that I can do, and they are, I can multiply these 2 things together, or I can add these 2 things together. And that, and the and versus or are basically, an and is another way of multiplying 2 things together, and or is another way of adding 2 things together. So if I say this matrix times this matrix, then I get out 1, 1, and then a whole bunch of other zeros. And that tells me this is the only habitat that's suitable for this critter. If my idea is it has to be far from a road, it has to be on sand, then an and statement or a multiply would be the way to do that. But there's another option, which is, well, it's better if it's away from roads and it's better if it's on sand, but like the critter could still survive on clay far from roads, and it could still survive like maybe closer to a road if it's on sand. It's just not as good for it, right? So that's an or statement, or an addition, right? So if I added these 2 together, then we get something that looks pretty different, right? We get a 2 and a 2, and then we get 1, we get basically like, what I made it so that you get like 1 everywhere else. But let's just imagine this was like clay or something. And we called this one a 0. I'll just turn that into a 0. Then you end up with this grid that's like 1, 1, 1, and a couple of 2s and some zeros. And so as you get more and more raster layers, you could imagine saying like, well, here's one where it like has to be far from a road, but whether it's clay versus sand, whether it's, you know, forest, wetland forest versus upland forest, whether it's, you know, some other categories that you think of, those are more fungible, right? Like they're not as critical that it has to be this thing. And that's where you can get to basically the addition, and you get a suitability analysis where it ranges from optimal to suboptimal. Okay, so let's see if I can. How did I do that before? Get me out of here. See if the annotation is still on there. Oh yeah, that looks good. Where was that? Oh, annotate was up here. Okay. Clear all dogs. Okay. Well, that's good to know that that exists as an option for later on when I want to draw on something, I guess, in a really awkward and horrible way. So here's an example of the main tool that you guys are going to be figuring out in lab this week and after spring break in lab 6, and that is raster calculator. And so raster calculator basically says whatever expression you put into that box, it is going to read out as a true false statement generally, or it's just going to add things together or multiply them together, whatever it is that you choose to put in. So in this case where you have this like DEM 250K, that's an awkward file name, but basically that's a topography file name. And what I've said in there is show me all of the pixels that are greater than 600, whatever the numeric value is, and output a new raster that just has values that are greater than 600. So basically with the new raster that comes out of this, all the values that are greater than 600 are going to have a value of 1, true, right? That's a true, whatever the statement is that you just gave me. And everything else that's less than or equal to 600 is going to have a value of 0. And so that is how you can create these binary maps, these sort of layers of suitability, if that's the direction that you choose to go for final projects too, of zeros and ones, or zeros, ones, and twos that you can use later on to combine to find those sort of optimal areas. So, okay, so where previously we have looked at vector analysis in terms of clips, or a couple of you have looked at intersects, but basically clip and intersect do essentially the same thing, the overlap between areas. In raster land, that looks like an and statement, or it looks like a multiply statement, where you say, find all of the places where raster 1 is true, so where it has a value of 1, and where raster 2 is also true, where it has a value of 1. That gives you basically the overlap. And just sort of like one thing to note in terms of these Boolean operators, in terms of multiplication, in terms of addition, or if you use an and statement or an or statement, anytime you have a value of no data in raster land, the no data carries through to the end. So be mindful of that. If you're trying to do some sort of multiplication and you have some no data values, and what you actually want those values to be is 0, not no data, then you can reclassify them. So you can reclassify this so that no data is just equal to 0. And that way, if you multiplied them together or did an and statement where both of them was true, you wouldn't have a no data problem at the end. Just to take you through and a little bit in terms of how this is different from a multiplication. So and basically looks for values that are non-zero. And it says, where are both of these raster grids non-zero? And if both of them are non-zero, this and this is non-zero, then it's true. If either of them are 0, so that's 1, the lower right-hand corner, 1 is 1, 1 is 0, that's false because they're this and this are both not non-zero. Similar to a multiply, if you have just ones and zeros that you're working with, and you're gonna get to play around with some of this stuff in lab too. And then last piece, this is one in vector analysis that you guys didn't really use, but it's called a union. So a union looks for the overlap of all of your polygons. So, give me the total area of all of your polygons and kind of puts them together. So that is effectively what the or statement, and the or statement is represented by this sort of vertical pipe thing for whatever reason, or the addition does that same thing. It says, okay, give me a value for anywhere that there's a value. I want, I want to know that it could be true in any of these different ones. So this is what an or statement basically looks like. It's also, if you've got multiple values in raster land, it's looking for only the ones that are 0 versus non-zero. So or says, all right, for this top left one, is either raster 1 or raster 2 a non-zero value? And the first one is a non-zero value, and so you're going to get out a true. Yep, one of those is a non-zero value. So the only cases where you would end up with a 0 value is like this upper right one, where that one's 0. Like neither this one nor that one is a non-zero value, so that's going to get a 0 at the end. Okay, enough of all of that crazy. I'm going to try to do a Kahoot with everybody online too. We'll see how that works. Exciting times. Where's my mouse? Okay, so there's your number. For those who are online, it is 496190. Kelly, can you see that online, the Kahoot?
I'm on the line.
Yeah, it's fine.
Yeah, I can see it.
You can see it. Okay, good, good, good. No cool music today because weird things happen when you have multiple things going on with Zoom at the same time. Okay, good. So off we go as far as the Kahoot. So 496190, and we're talking about raster calculations. So 1 and 0. All right, so the and statement, and we just went through this really quickly. So an and statement says that in order for the answer to be true, and true means 1, then both of those two values must be non-zero. So the only time where you would get an answer of 1 from an and statement is if both of them are 1, or one of them is 1 and the other is 2 or 3 or 500 or something that is not 0 or no data. So good. All right. So the or statement is next. All right, nice work, guys. Yep, so the or statement says, as long as something in there is non-zero, that's going to be true, and 1 equals true. Nice work. Little change, and they've got like little stock market things going on in here, huh, to see where everybody's going. All right, so this is a weird one in terms of the or and the and statements. Ors and and statements, those Boolean operators, only ever give you answers of 1, 0, or no data. That's the only thing that they will ever give you. So 1 is true, 0 is false, and no data is somebody had no data in whatever that pixel is. So if you have a statement of 4 or 1, then basically that says, are either of these non-zero? And if the answer is yes, in fact, both of them are non-zero, right? Then you're going to get a true at the end of that, and true is represented as a 1. All right, nice work. Moving on up. All right, good. So anytime you've got no data in the mix, then you're always going to end up with an answer of no data at the end. That is an issue, because if you create, for example, like a distance grid away from something, sometimes you'll limit it to just so far, something like that, and you end up with no data further away from that. If you still want to consider those pixels out there in your suitability analysis, then you're going to need to reclassify them as zeros or as something else so that you can actually operate them. So anytime you try to do an and operation, an or operation, an addition, or a multiplication with no data, you're always going to get no data. Nobody likes my 42 answer, huh?